Both the Boeing 747 and the Airbus A380 are known as the titans of the sky. They have rewritten the rules of long-distance travel. The 747's engines represent a half-century of evolution, upgraded again and again to keep the icon alive. The A380's engines, by contrast, were designed from scratch. So how do these power plants compare? Let's peel back the cowling and explore the incredible engine differences that powered two of aviation's greatest rivals. The Boeing 747 first rolled out in 1969, a product of Cold War ambition and airline expansion. At the time, the goal was simply to build a jet that could carry hundreds of people farther and faster than anything before. Engines like Pratt & Whitney's JT9D were selected for raw thrust, not efficiency. Fuel was cheap, regulations looser, and airlines wanted performance above all else. By the 2000s, things had changed. When Airbus launched the A380, the aviation world demanded low emissions and noise with maximum efficiency. Airbus designed the A380's power plants, namely the Rolls-Royce Trent 900 and Engine Alliance GP 7200 for a different age. These engines had to deliver huge thrust while also sipping fuel and keeping passengers comfortable. The Airbus A380 stands as the heaviest passenger jet ever built with a maximum takeoff weight of about 1.2 million pounds. To lift it, Airbus gave airlines the choice between the Rolls-Royce Trent 900 or the Engine Alliance GP 7200. Both produce between 70,000 and 76,500 pounds of thrust each. Multiply that by 4 and you get nearly 300,000 pounds of force at takeoff. The Boeing 747-8, the final passenger version, uses the General Electric GEnx-2B67. Each delivers about 66,500 pounds of thrust. 4 together produce about 266,000 pounds. Slightly less than the A380, but still enough to lift almost 1 million pounds into the sky. But more thrust doesn't always mean more efficiency. The A380 needed brute force to move its massive frame. The 747 relied on engines tuned to balance thrust with fuel economy. One is raw muscle while the other refined power. Both giants use high bypass turbofans, but the way they apply the technology differs. The A380's Trent 900 operates with a bypass ratio of about 8.5 to 1. That means for every 1 unit of air going through the hot core, 8.5 units go around it, which leads to the production of cooler, quieter thrust. The GP 7200 sits in the same range, designed jointly by General Electric and Pratt & Whitney to meet Airbus's demands. The 747-8's GNX engine pushes the ratio higher to around 9 to 1. Larger fans move more cold air, creating thrust more efficiently than hot exhaust alone. This leap made the Boeing 747-8 burn about 15% less fuel than the older 747-400, even though the plane itself was bigger. So, which is better? Airbus achieved silence and strength, while Boeing stretched efficiency to its limits. The battle is more than just numbers. It's how you use bypass technology to solve different challenges. The A380 was marketed as the most efficient aircraft per seat in history. At full capacity, which is more than 500 passengers, it consumed about 3 liters per 100 kilometers per seat. That's better than many small cars. But the catch was that few airlines consistently filled it to the brim. An underloaded A380 became a fuel guzzler. Economics undercut its engineering. The 747-8's smaller size made it easier to fill, and its GEnx engines delivered competitive fuel burn. On many routes, the per-seat efficiency of the 747-8 came close to, or even beat, the A380 when the Super Jumbo wasn't full. On average, the 747-8 was burning 2.8 liters per 100 kilometers per seat. This is the irony of aviation design. The most efficient aircraft on paper may not be the most efficient in practice. Another arena is sound and what passengers actually hear and feel inside the cabin. If passengers had to pick one clear winner, it might be the A380. Its engines are among the quietest ever fitted to a large jet. Rolls-Royce used swept fan blades, acoustic liners, and low-pressure cores to reduce cabin noise dramatically. Many passengers describe the A380 as so quiet it feels like gliding. The 747-8 also shines here. Chevron nozzles on its GEnx engines mix hot and cold exhaust flows, which reduces noise and vibration. For those who remember older 747s, the 747-8 is whisper quiet by comparison. But head-to-head, the A380 edges out Boeing. Its double-deck cabin and acoustic design gave passengers the smoothest ride ever offered in a wide-body jet. And while comfort wins passengers, airlines look at something else entirely. Airlines judge engines by how often they break down and how expensive they are to fix. The A380's engines had teething problems. In 2010, a Qantas A380 suffered a dramatic Trent 900 failure shortly after takeoff from Singapore, scattering debris across Batum Island. The fleet was grounded until modifications were made. Rolls-Royce strengthened turbine components and improved oil feed systems. Though reliability improved, airlines had to foot high maintenance costs. The 747-8's GEnx engines, meanwhile, benefited from years of development for the 787 Dreamliner. Composite fan blades and modular systems made them easier and cheaper to service. Airlines praised their consistency and lower operating costs. Engineering ambition often comes with risks. Airbus pushed boundaries with the A380's engines, while Boeing leaned on proven technology refined for reliability. The A380's engines boast a fan diameter of about 116 inches. The GEnx fans on the 747-8 measure about 105 inches. That 11-inch difference might not sound like much, but in engine design it's huge. The A380's wings were designed from the start to carry massive engines with fans over 9 feet wide. Bigger fans move more air, which improves bypass ratios, lowers fuel burn per seat, and keeps noise down. The Trent 900 and GP 7200 fit that mission perfectly, even if they were heavier and more complex. Boeing, on the other hand, faced constraints. The 747's wing design dated back to the 1960s. Ground clearance under the wings limited engine size without expensive redesigns. Instead of chasing the biggest possible fans, Boeing optimized within tighter limits. The GEnx engines used advanced composite fan blades and higher bypass ratios to squeeze maximum efficiency from a smaller footprint. These choices reflect what airlines wanted from each jet. Carriers buying the A380 wanted to move as many passengers as possible on slot-restricted routes, and they were willing to accept higher maintenance. Airlines choosing the 747-8 valued flexibility. They wanted a jet that could serve many airports, fill more easily, and deliver solid efficiency without needing record-breaking fan size. But the real test of any engine is how it pushes a fully loaded jet off the runway and keeps it cruising across oceans. The A380's engines lift a super jumbo weighing over 1.2 million pounds. Yet takeoff feels surprisingly smooth, with acceleration steady rather than explosive. Once airborne, it cruises at Mach 0.85 with ease, carrying more passengers farther than any other jet. The 747-8, at about 987,000 pounds maximum takeoff weight, is lighter but still formidable. Its GEnx engines give it brisk acceleration and strong climb rates. It also cruises near Mach 0.85, matching the A380's speed despite having less thrust. But flight performance is only half the story. The other half is environmental impact. Both aircraft faced growing scrutiny over emissions. The A380's engines met all ICAO standards, but 4 large power plants inevitably produced more harmful gases like carbon dioxide and nitrogen oxides than smaller twins. Airbus argued that per-seat emissions were low when full, but again, only at maximum load. The 747-8's GEnx engines were designed to cut particulates and burn cleaner fuel. They reduced NOx emissions by about 30% compared to older models. Still, neither 4-engine giant could match the efficiency of new twin jets like the A350 or 787, and that sealed their fate. Environmental economics favored smaller twin-engine aircrafts. This brings us to the final chapter of their story, the legacy their engines leave behind. The Airbus A380's engines powered the largest passenger plane in history. They proved that it was possible to lift an airborne hotel with unmatched quietness. But their complexity and cost made the A380 less attractive to airlines, leading to its retirement from production in 2021. The Boeing 747's engines tell a different story. From the JT-9D in 1969 to the GEnx in 2023, they chart aviation's entire modern history. Each upgrade squeezed new life into a design that seemed destined for retirement. The final 747 rolled off the line in 2023, closing an era but leaving a legacy of adaptability. So, which engines win? The engines of the Airbus A380 and Boeing 747 reveal two visions of aviation, one built for scale, the other refined for endurance. One was bold but short-lived, the other adapted and endured for over 50 years. Together they show how engineering choices shape history in the skies. For more than half a century, airlines and engineers have been locked in a race to build bigger, faster, and more comfortable passenger jets. From the sleek elegance of Concorde to the double-decked Airbus A380, these machines were built to change the way the world travels. But how do you even build something the size of a skyscraper and send it safely into the sky? Today, we're going inside the workshop to see exactly how the 10 largest passenger jets in history were made. We'll follow them in historical order, not size, to see how each generation pushed the limits further. The Boeing 707 was the plane that replaced propeller planes and made long-distance travel much faster and easier. At 46 meters long with a 44-meter wingspan, it carried about 180 passengers in early layouts. Its fuselage was built from conventional aluminum alloys, joined by riveting techniques honed during World War II bomber production. The wings were reinforced with steel spars, while titanium was used sparingly in high-stress fittings. The JT3D turbofan engines were podded under the wings, which reduced cabin noise compared to earlier turbojets. Engineers developed modular wiring looms and hydraulic systems that could be rapidly installed. Inside, engineers designed a circular fuselage cross-section, strong enough to hold pressure at high altitude to give passengers a quieter ride compared to propeller aircrafts. Air conditioning packs and sound insulation were integrated beneath the floor, which made long intercontinental flights more comfortable. At 62 meters long with a 25-meter wingspan, Concorde carried only about 100 passengers, but at twice the speed of sound. Built from aluminum alloys capable of withstanding 127 degrees Celsius skin temperatures at Mach 2, the fuselage expanded several inches in flight. Engineers designed sliding joints and flexible wiring harnesses that could stretch with the airframe. Titanium was used in heat-critical areas such as the engine nacelles. The delta wings were built in sections and joined with precision drilling to optimize both supersonic cruise and subsonic stability. Concorde's fuel system was one of its most unique engineering feats. Pumps shifted fuel between tanks mid-flight to balance the aircraft's center of gravity as it accelerated through the sound barrier. For passengers, Concorde meant a 3-hour flight across the Atlantic in unmatched luxury, though cabin size was sacrificed for aerodynamic efficiency. The L-1011 TriStar was one of the most technologically advanced jets of its era. It measured 54 meters long with a 50-meter wingspan and seated about 270 passengers. Its fuselage was made from precision-machined aluminum lithium alloys, with titanium used in the landing gear and engine pylons. One of the most innovative features was its autopilot and auto-land systems, which were integrated during assembly with redundant wiring looms and hydraulic circuits. Engineers also optimized the wing with advanced high-lift devices which were installed using laser-aligned jigs for accuracy. The Rolls-Royce RB211 engines required composite fan blades. Though costly, they gave the aircraft quieter performance compared to rivals. Passengers enjoyed smoother and quieter rides, which gave it a reputation for comfort that outlived the jet itself. The DC-10 was another tri-jet that measured 55 meters in length with a 50-meter wingspan and seated around 270 to 300 passengers. The fuselage was built primarily from conventional aluminum alloys, but engineers reinforced the lower lobe with titanium fittings to handle the stress of its unique third engine mounted in the tail. Riveting dominated assembly with tens of thousands of fasteners joining the large fuselage barrels. Modular wiring harnesses and pre-installed hydraulic lines sped up production. The later MD-11 introduced composite materials in control surfaces and winglets to improve efficiency. Extended range versions required redesigned fuel systems with pumps capable of handling higher flow rates across multiple tanks. For passengers, the DC-10 and MD-11 offered wide cabins and long-haul capability, setting a standard for international travel in the late 20th century. Russia's answer to the wide-body race, the Il-96 combined traditional metal construction with selective use of composites. The fuselage was built from high-strength aluminum alloys with carbon fiber panels and control surfaces to save weight. Titanium was widely used in landing gear and engine pylons. Its sections were built in Voronezh and joined using hydraulic jigs and robotic riveters. The jet measured 65 meters long with a 60-meter wingspan and carried up to 300 passengers. Il-96's 4 PS-90A turbofans engines were equipped with wide-chord fan blades, giving it quieter performance than earlier Soviet aircraft. Engineers also installed advanced avionics and redundant fly-by-wire controls for improved safety. Passengers experienced a quieter, more comfortable ride compared to its predecessors, though the Il-96 never achieved widespread adoption outside Russia. The A340-600 was one of the longest passenger jets ever at nearly 76 meters. It had a wingspan of 63 meters and could carry up to 380 passengers. The fuselage was built from high-strength aluminum alloys reinforced with titanium in the wing roots. Engineers designed the wings with composite spoilers and winglets to reduce drag. Assembly involved modular fuselage sections built in different European plants, then transported by Beluga aircraft for final joining in Toulouse. The 4 Rolls-Royce Trent 500 engines were mounted on pylons, designed with titanium fittings to absorb vibration and thrust loads. The long fuselage required additional fuel tanks and a reinforced floor structure to handle passenger and cargo weight. Inside, airlines could configure luxurious layouts with spacious cabins. For travelers, the A340-600 offered long, non-stop flights without refueling, though at the cost of higher fuel burn compared to later twin jets. The A350-1000 represents the cutting edge of composite passenger aircraft design. Nearly 53% of its structure is carbon fiber reinforced polymer, including the entire fuselage and wing panels. This dramatically reduced weight compared to traditional aluminum. The wings were designed with a unique curve that automatically adapts in flight, improving lift and reducing fuel burn. Each was assembled using automated fiber placement machines that laid down precise strips of composite tape before curing them in massive autoclaves. Titanium was used in landing gear and engine pylons to handle high-stress loads. The Rolls-Royce Trent XWB engines were integrated with nacelles designed for laminar airflow to reduce drag and noise. Passengers experienced quieter cabins, larger panoramic windows, and LED mood lighting. Airbus also installed advanced air filtration and higher cabin humidity levels to reduce fatigue on long flights. The A350-1000 demonstrates how material science and production automation can directly shape both efficiency and comfort. The Boeing 777-300ER is among the largest twin-engine passenger aircraft ever produced. It has a length of 74 meters, wingspan of 65 meters, and could carry 396 passengers. Building such a giant with just 2 engines demanded radical material and design choices. The fuselage is built from advanced aluminum lithium alloys that combine lightweight with fatigue resistance. The 777X goes further by using the largest composite wings ever built for a passenger jet. These wings were cured in giant autoclaves and feature folding wingtips, so the jet can fit into standard airport gates. Assembly lines were reorganized around modular sections. Pre-wired panels and pre-installed hydraulic systems were snapped into place to reduce production errors and speed up final assembly. The GE90 and GE9X engines, the most powerful turbofans in history, were built with ceramic matrix composites capable of withstanding higher temperatures, boosting efficiency. For passengers, the benefits were clear. Longer non-stop routes, larger windows, higher humidity levels in the cabin, thanks to improved fuselage sealing and lower cabin altitude. These engineering choices made ultra-long-haul flights more comfortable than ever. The Queen of the Skies was stretched to new limits in the 747-8, the longest passenger aircraft ever built at 76 meters. Production took place at Boeing's Everett facility, the largest building in the world by volume. Fuselage sections were built from high-strength aluminum alloys and riveted together using robotic systems capable of drilling and fastening with millimeter precision. Engineers redesigned the wings with raked tips and integrated composite panels that cut drag and improved fuel efficiency. The engines, GEnX2B67, adapted from the 787, featured composite fan blades and titanium leading edges. Not only did they improve range, but their quieter operation directly improved the passenger experience. Inside, Boeing introduced mood lighting with larger windows and a redesigned upper deck for more premium seating options. By sticking with 4 engines, Boeing ensured redundancy and long-range reliability, crucial for airlines flying intercontinental routes. The 747-8 showed how incremental engineering improvements could keep a 1960s design competitive in the 21st century. The A380 is the undisputed giant of passenger aviation. With 2 full decks, it can carry over 850 people in an all-economy layout, but building it required some of the most complex engineering in aviation history. The wings alone stretch nearly 80 meters larger than many regional runways. Each was manufactured in climate-controlled factories in the UK, where automated laser-guided drills installed thousands of titanium fasteners. Carbon fiber composites were layered into the wing box to save weight, while high-strength aluminum alloys provided rigidity where loads were greatest. To handle the stress of long flights, engineers integrated an intelligent fuel system across the wings. Pumps automatically transferred fuel between tanks to balance the aircraft mid-flight, keeping it stable despite its massive size. Inside the fuselage, modular wiring looms were pre-assembled on the ground, then plugged into place during final assembly. This simplified what would otherwise be a tangled mess of over 500 kilometers of cabling. The high-mounted wings and engines pushed farther from the cabin reduced vibration and noise, creating the quietest cabin of any large jet. Airlines took advantage of this by fitting lounges, bars, and even showers. Though production ended in 2021, the A380 remains a symbol of pushing engineering to its limits in the service of passenger comfort. So, what do these aircrafts tell us? Every generation of passenger jet has tried to stretch the idea of how many people a single aircraft can carry. Some became icons, others faded into history. But here's the question. Have we already seen the peak of the passenger super jumbo, or will the future bring something even larger than the A380? If you enjoyed this look at the giants of the sky, don't forget to like, subscribe, and stay tuned, because the next chapter in passenger aviation might be closer than we think.